Hello everyone, this is Shashank Modi from CAR. There are still people joining in. We will just wait a few minutes before starting it, so please wait for a few minutes. Thank you.
Yeah. Yeah. Yeah, I can't hear anything. You guys talking? Okay.
Hello, this is Ravi here from ALTAIR.
Hey Ravi, this is Shashank.
Yeah, and this is Abe. Yeah.
Started. We have people online.
Let's see. Do we have Dave online?
That's what I'm trying to.
Okay, because he may be caller 2 for all we know. Dave Derbyshire, are you online?
Okay, let's start with Ravi anyway.
Yeah.
Can everybody hear me? And we'll be sharing the screen. So I just unmuted everybody. Just let me know if you can hear us well and see the screen.
I can hear fine.
Okay.
Okay.
Very good. Why don't we get started? We have the pleasure of having Ravi Kunju from ALTAIR, as well as Dave Derbyshire from DASI. I'm assuming he's online or will join us shortly. And here they are. And my name is Abe Wadhawker. I'm the Director for Manufacturing, Engineering, and Technology here at the Center for Automotive Research. And Shashank, you want to introduce yourself?
Yeah, my name is Shashank Modi. I'm a research engineer at the Center for Automotive Research. And work for the Coalition for Lightweighting Materials Group. And my research is focused on lightweighting trends and advanced manufacturing technologies.
Lately, there's been a significant amount of interest in additive manufacturing, or as it's also known as 3D printing, for many different applications in not only automotive but other industries as well. In different ways. One of the ways is as far as parts for the vehicles, and then tooling as well. So, and there are many facets to this exciting technology that we think that you will learn a lot, and hopefully you will have a lot of questions as well. So why don't we get started with Ravi? Ravi, if you are online, please.
Yeah, Ravi, I will make you a presenter, and then you can share the screen.
Okay. Sure. All right.
All right. Okay, you should be able to present. There we go. Outstanding. I love it when technology works.
Yeah, so do I. And I presume you can see my entire screen without any problems, except the go-to screen on the right-hand side, which unfortunately you can't get rid of.
And before Ravi, you start, I just want to mention that if the live audience, if you have any questions, you may submit it to the chat option. There's a chat button on your GoToMeeting. Just write up your questions there, and we will discuss it in the Q&A session. Also, I want to say that we will be recording these webinars, so all the car affiliate members will get a link so that you can refer to them at the later stage. Ravi?
Fantastic. Thanks, Abe and Trishank, for the introduction. And I presume I have about 15 minutes, and I'll try my best to cover additive manufacturing solutions from where we come from, and where I see it, and what we are doing there. So hopefully this presentation will give you a quick overview of what's going on in the additive space, what are the challenges, and what exactly are we doing as a company to address these. Having said that, let's get started. The challenges of designing anything innovative, like what you're seeing on the screen, which is not an automotive component, but it's extremely important to put automotive things into perspective or make them. This is a robotic arm, and the idea here is, the reason I'm showing you this is I'll build on that story in the next few slides. Whenever you're making anything complex, something as complicated as an automotive, it's always a combination of balancing between the power, the speed, the accuracy, the strength of this gripper in this case, versus the weight. And at the end of when it comes to weight, it's not just the overall weight, but also the distribution of the weight in itself, so that there's balance in the component, there's efficiency in the design. And at the end of the day, when you have all these things coming together, you also want to make sure that the cost of manufacturing it and the ability of manufacturing it are within the controls of what you set up your ideas with. So it's always a balance between these. And the promise of additive manufacturing is that it gives you a tremendous amount of geometric freedom. You are pretty much free to determine what you want with respect to how you can print them. But of course, there's a lot of other challenges that we'll talk about in the next few slides. And the other important aspect is, in addition to getting geometric freedom in your design to print, 3D print any types of shapes that you are not restricted to with undercuts and others, there's also a lot of possibilities for doing part consolidation as well, where you can put more than a few parts together to make one component and reduce a lot of post-manufacturing and fabrication issues and dimensional accuracy and so on and so forth, and tolerances. And again, the idea here is to create accelerated product development than before. If you have a good understanding of the performance requirements, then you can rapidly create something much more quickly than the traditional process, which just can be time consuming in terms of trial and error, build of tooling, and other aspects. And then the fourth aspect is also design individuality, meaning that you can create components that are very specific for a specific purpose. The bracket that you see here is of architectural beam. It's basically a joint and a truss and was developed with Uwe Arup in UK. Very complex structure. Lots of parts were consolidated into one. There's a tremendous amount of weight bearing that goes into it, but it's very structurally aesthetic. and also a very critical component, and it was all done in one shot. So, meaning that under certain specific conditions, you can create specific products for specific purposes as well. So these are tremendously, obviously, the promise of additive manufacturing. And what are we doing here? So let me give you an idea of topology optimization, and which is basically a kind of a generative design which dictates how shapes grow based on performance requirements. So let me use this AP Works, the bike that you see, which was first conceived, which is a joint project between Airbus, ALTAIR, AP Works, which is a subsidiary of Airbus, ALTAIR, EOS, and this was an electric motorcycle, and the idea was to try to see how much we can reduce the weight of this, and considering all the performance requirements. And this to set the context of what we are doing here as well. The first in this design, in this process, is to understand. I don't know if you can see my video coming up on the screen. This is basically excellent. So here you're looking at the bike frame, how it was built, and we'll go over the process of how exactly this was put together. So the idea is first to start off with a design space, which is basically your operational space within which you want to grow a structure. And you also identify certain non-design space which you do not want to touch. For example, maybe something for a wire harness or a bracket mount. And then once you've identified the design and the non-design, the next is to identify the loads and the boundary conditions. What are the boundary conditions? What are the ideal loads? And you need to extract it from various other forms of either simulation or tests. And then you run through an optimization process, and the optimization automatically generates a topological shape based on any manufacturing constraints that you might have given. The only constraint I was given in this particular case was symmetry boundary conditions, symmetric conditions, so that it grows symmetrically about a particular axis. And once you've generated that shape, you can put that shape back and reanalyze it and make sure that it's performant based on the original performance requirements that you had given. So the process is you take the shape, you extract the, you create a design shape, and then you extract, let the topology optimization generate the shape automatically, and then come up with a particular shape with it. And then you put it back into performance. And what did we achieve here? This was, of course, for us to push the limits of what we could do. In this case, the entire frame of this electric bike is only 6 kilograms in total weight. There's special materials developed for this as well. And it was a special titanium alloy that was made for this particular purpose. And there was a lot of work that went into basically producing this vehicle, in addition to the topology optimization structure that you see. And the overall weight of this vehicle is 35 kilograms, and it will go as fast as 80 kilometers an hour. So this is what is possible. And again, over the last 15 to 20 years, when ALTAIR introduced optimization through OptiStruct, we have hundreds and thousands of customers across the world using it on production products every day, every single day. This is some examples that you're seeing right here on the screen. And right from very different applications, you see a bike frame, you see a piston head, you see an aerospace bracket, you see an antenna bracket for RUAG, which is actually circling the Earth today. And then you can see multiple different components. I just wanted to put that together. And all of them, you achieved not only performance requirement, you meet the performance requirements, but also tremendous weight savings as well. And this is the promise of topology optimization that we have brought into the world that everybody's using on a daily basis. So what is the potential here? Again, stretching it into the automotive side, this is another project that we did, again, with AP Works and as well as EOS and others. The idea was, how can we optimize an entire front structure for an existing vehicle, considering not only all the loads here, in this case, the crash and stiffness, all of them were taken into account to build the topological structure, and then it was additively manufactured. And again, the structure has multiple purposes. Not only the ability to absorb the crash in the most optimal way, and also meet the frequency requirements and the structural requirements, but it also provided relief in terms of passive and active cooling as well. You could see the pins were built into it for a passive thermal management, and the structure itself was hollow, so it would also carry the coolant, the brake fluid, and the coolant in two different chambers as well. So both supported both active as well as passive cooling as well. And this was a work. It is definitely a piece of art, but at the same time, it is pushing the limits of how much you can, how much freedom you have to create extremely innovative designs, like you're seeing, that meeting multiple purposes in one shot. This is all the parts that were printed, just to show you some pictures. Obviously, there are multiple parts printed together and then welded together. There's a fair amount of fabrication that was done in this case as well. But the structure is beautiful, it's organic, and completely optimized to meet the requirements. Now we've also extended this into a formal process called a C123, where we basically break this entire for vehicle for creating innovative design concepts. We identify the optimal structural layout using freeform models, create the baseline shape, and then the C2 is basically rapid optimizing, sizing the joints, and also creating the joints for using low fidelity models, and then finally putting it all together and doing the optimal case in the C3 stage with the actual joints using high fidelity models as well. So this is the process that many automotive the companies around the world are starting to look at, and this is again the organic shape that you would have never imagined without the use of computers, and a lot of potential to use additive manufacturing, and especially in the joint areas for making those joints as well. And just a plug-in for our ALTAIR Technology Conference, which will be on the 16th to the 18th in Paris, and Andrea Marula from Ferrari will exactly talk about the C123 process at the conference as well. So very exciting for us to see everything coming together, the topology optimization in a full vehicle, and you can see the Ferrari's presentation at the ALTAIR Technology Conference in a couple of weeks, covering this particular, how everything came together here. So having said that, what we have done is, this is a chart that shows you the advent of CAD, 3D CAD, from the 80s, 90s, and the 2000s, and to current day. And you could see the 3D CAD started growing at the cost of 2D CAD, right? In the 80s, 3D was just coming in, 3D CAD was coming in. But towards 94, towards the end of 90s and the beginning of 2000s, ALTAIR introduced OptiStruct into the market. And that's when simulation-driven design started. The simulation-driven design started to come into the hands of the CAE community, where performance and manufacturing constraints were driving the design rather than you taking a design and validating it. So this started this whole red strip that you see in this chart of simulation-driven design, which is catching on very, very strongly. And especially then in the additive side, it's extremely important because there's tremendous amount of freedom that you have, and you can influence it up front. So what we did was, when we brought this, it was in the hands of high-end analysts and high-end engineers in the form of OptiStruct, but then we figured out that it was too late in the process, so we wanted to bring it up front into the hands of designers. So we put it in a platform called Inspire, where designers could access the same technology but up front and with very easy to use environment. And that was the advent of this. And so we had to ask ourselves the question, what are these designers in addition to topology would want? So we break this down into three parts. One is system modeling. So we have a whole set of math modeling tools that can capture all the performance requirements. So you can take all your loads from multidisciplinary analysis or requirements that you have, extract those loads into from a very high-end system-based modeling environment that we have. And once you extracted those loads and performance conditions through the baseline system modeling and system that you've built, you can then convert them into three-dimensional shapes, whether depending on what the manufacturing process is, whether it's additive, whether it's traditional manufacturing process, and then so you create these three-dimensional shapes from it. And then once you've done that, you also want to make sure that they're manufacturable. So all of them we put together in one environment, which is the Inspire. And here what we are trying to do is, it's very important to analyze that the three things that we identify are the performance, manufacturability. How can we put these two things together and then make sure that we create efficient designs that take performance and manufacturability together to create efficient design? And then once those designs are coming in, you want to take them back and then see whether they are manufacturable and are able to perform under the conditions. So this is where you want to create one environment to analyze, generate, and simulate all your designs so that it's early on in the design process so that you understand the manufacturing defects and the problems as well. Having said that, we introduce Inspire. We're coming into additive in a second, but the idea here is to be able to sketch, to render, to visualize, to create structures and extract loads from the motion simulation and kinematic simulation, extract the loads and create structures that are manufacturable, and at the same time go as deep as possible into the manufacturing processes as well, whether it's casting, injection molding, sheet metal forming, metal or polymer extrusion, and as well as additive manufacturing, which is what we're going to look at in the next few slides. So we put it all into one environment. So whether you're doing casting, forming, or whatever have you, whether doing additive manufacturing, you can bring in a component, for example, that you've generated based on the criteria you've described. You can create the support structure without having to go to multiple tools. You can create a support structure within this environment. And once you've created support structure, which is all geometry, you can not only create the support structure, but you can also go and do the simulation, the numerical simulation, the build simulation after that within one environment as well. So the idea here is, to be able to provide to the end customers the ability to conceptualize the designs based on the manufacturing requirements as well as the performance requirements, and be able to go as deep as possible into the manufacturing feasibility arena, and the performance arena, so that it can put the part back into performance and see whether everything is coming together. That's what we are doing. So let's put this into context about how this works in the additive manufacturing process flow. Again, you have requirements. You take those requirements and you create the baseline topology shape, which is basically what I call as a rock candy. And from the rock candy, you create beautiful surfaces using our polyNURBS. And then once you've done that, you can go to the build preparation and drive your simulation, build simulation there, and verify the entire process. So let's look at it from a context of how actually it plays. So here I'm showing you how this entire tool chain works in the context of showing you a bracket. This is the original design. You take the original design and you extract the loads on the performance loads, and you first want to do a baseline run and see whether you can extract exactly the performance requirements. Because the idea here is not only are you creating the first baseline run, but you're taking that and creating a design space and then extracting the topological shape out of those requirements. And then once you've created the rock candy, you can use the polyNURBS to wrap around and create solid, nice surfaces that you're seeing on the screen. And then you can modify those designs and put certain features in there as well. And once you have them, you can put that design back again, reperform, and then also evaluate, put it back into the manufacturing process. In this case, you're orienting the part. You're basically saying, okay, I'm orienting this part. I'm going to create a support structure, and I'm just going through, not only have I designed the part, but I'm creating the support structure and also doing the performance evaluation of this as well. So all in all, doing the whole process simulation, creating first the designs that are cognizant. And in this case, you take out the old part and put a new one where the stiffness is 52% higher, mass is 58% less, and the fatigue performance is much higher. So you basically take the old part and put a brand new additively manufactured component in there as well. So what is the path to serial production? I mean, there, in my opinion, there are two things. If the path to serial mass production for additive manufacturing is you need to make sure that you create manufacturing constraints so that you create designs that are free of, let me stretch it. If you can generate designs that do not require any support structure, that means you're not doing any post-processing, that you can take it out of the printer, maybe do some heat treatment, and then it's ready to use, which means you have to create those structures with those manufacturing constraints. So there's no post-processing operation. The second is if you're able to build the whole thing, the entire structure, without distortion, to me, if you're achieving those two things, zero support structure and zero distortion, that's the path for serial production, where additive manufacturing could come to this to automotive volumes. Okay, today automotive, they're using it for prototyping and so on. But if you want to go really fast and very high volume, these are the two things we want to achieve: zero distortion and zero post-processing. Having said that, we have tremendous amounts of. Yep, sorry.
Ravi, a couple more minutes, if you can wrap
sure.
up.
Yeah.
Okay,
so basically, I think it's important to understand that we have also introduced. We have tremendous amount of manufacturing constraints that you can bring to the table, but to drive the designs in a particular path. And I think it is essential to understand. One thing is when you're doing these kind of analysis and creating this, if you don't understand the manufacturing constraints, my advice is do not do topology optimization. But in this case, we have introduced overhang constraints that basically allow you to generate designs that are free of support structure. And I'm just zipping through this, where you can specify and create structures. For example, you see these tear hole shape because you're forcing it to create structures that do not have any support structure at all. And having said that, we can also do the whole numerical simulation, as I pointed out earlier, whether tracing the path so that you can control the distortion as far as you can. So if you can create designs that are support-free and also distortion-free, that's the path for creating production volume, production intent volume of production with additive. Again, I'm showing you some examples here of what we have done, and also to put this in perspective, jointly with CAR, the Enlighten Award winners this year were BMW, and they basically created industry's first serial production part using OptiStruct and ALTAIR's technology and Inspire to create, using overhang constraints, to create this particular part that you're seeing on the screen that required no supports. It's just heat treated. They make 300 of them in one batch, and it's the first production part. It's on the I-8 of the, it's a roof latch, roof bracket, and it's on the BMW today. And again, they're presenting on our ALTAIR Technology Conference in Paris. And if anybody of you are dialed in or going to attend, we will make those presentations available as well. Again, there are a lot of other challenges as well. Other challenges for adding more manufacturing constraints, including distortion, thermal distortion, and controlling the thermal overheating in certain areas. The challenge is always all on the chamber size. You're always limited by the size of parts that you can make, and also the quality and the component finish, amount of post-processing that you'll have to do. And again, certification, which is again a big challenge for the entire AM community. And we're working towards all these areas as well to make sure that we understand not only the build process to generate the designs, but also to capture the entire manufacturing process simulation as well. So in summary, mass production of AM has not yet impacted automotive and aerospace for mass production, but it's coming slowly, as shown by the BMW bracket. And again, large-scale AM is being tested, and we definitely feel that topology optimization is a key technology for generating the product differentiation required for additive manufacturing. With that, I'll hand it over back to Shashank.
Okay. Thank you, Ravi. That was fascinating. Really appreciate that. And I think we have Dave Derbyshire online now. Let's see. Do we?
Yes, this is Dave Derbyshire.
Yeah. Yeah. Good afternoon, Dave.
Let me make you the presenter. till then, let's, if you can introduce yourself.
Yeah, go ahead and introduce yourself, and in the meanwhile, we'll get you set up so your screen can be seen.
Okay, can my screen be seen at this time?
Not at this time. Let me make you the presenter now. Okay, I made you the presenter.
Okay.
And you should see it.
Yep.
There we go. Yep, we see it.
Okay, great. Thank you very much. My name is David Derbyshire, and before I even get started here, I would like to compliment Ravi on the presentation that he had done. The most important thing that we need to recognize when it comes to 3D printing or engineering design processes is everything is interconnected. If you don't have a good design and you don't understand the ultimate, you're going to run into a little bit of problems. Am I still being heard?
Yeah.
Hello?
Yes, we can hear you.
Okay, sorry, I heard someone say unmuted. Anyways, so the challenge that we have right now is having a better understanding as to what is additive manufacturing and what is it, how does it play a role in the output and also the design's decision-making processes, as what Ravi has discussed earlier. Some of the big challenges that we have in additive manufacturing is people not having a proper expectation as to what 3D printing is able to produce as either a concept model or as a finished product. And that is the whole issue that the entire industry is trying to face today. 3D printing, additive manufacturing is affecting every industry. Everywhere you go, it is a topic of conversation, and big decisions are being made as to whether or not people want to bring the capabilities in-house, leverage outside resources, how can they take advantage of lessons learned from other industries and apply it to their market segment. Because at the end of the day, what is happening in the automotive and aerospace industry is being driven in some practices by the medical and toy and consumer product marketplaces. Now the big question comes into play is to how is this industrial revolution going to affect your specific business or your organization? Desai Solutions as a company, we've been around since 1995, and primarily we've been support organizations to companies like ALTAIR Engineering in helping companies implement design and engineering software that can help bring products to market faster. And with the advent of 3D printing, we don't need to say it's the next industrial revolution. It is already here. 3D printing has been widely available since 1989. The big things that have changed is the methodology for what is called 3D printing. And in the space of Desai Solutions, the bulk of our experience has been in the form of what's known as PolyJet and FDM or fused deposition modeling. And for those that are relatively new to 3D printing, and sometimes I have to say, you have to assume that everyone has been exposed to it, but then again, you have to understand the differences of the different technologies in the material delivery systems, because that can directly impact what machine or what system or what process you ultimately use. And in the world of 3D printing, there are primarily two different types of technologies that are being widely deployed out there in the marketplace. One of them is a form of what we call traditionally the PolyJet market, which is where you're using a jetting system to layer material down and then using an outside curing source to change the material from one state to another. In some situation, it's a powdered metal to a fixed metal, or in another situation, you're doing a thermoset type operation or using thermoplastics to actually melt the material and deposit it down to where you want it to be. The challenge that you have is in these different types of application is not necessarily what's happening to the part on the build cycle, but what happens to the part after it comes off the machine. Each technology that you deploy, whether it's PolyJet, which requires a different type of post-processing and interaction that could impact the ultimate deliverable for the person, has to be taken into consideration. For example, in the PolyJet scenario, the materials are being laid down and you don't have to worry about concerns of thermal stresses and shape shifting and materials not interacting properly with their support material. Or in the case of FDM, you do run into a bigger problem where problems such as when the part is cooling down, are you getting sink marks that are showing up in the part? Are you burning off support material? Are you using a chemical to change the state of the process? Are you doing a lot of post-processing? And then ultimately, what do you do with the part once it goes through these post-processing operations? So all these things must be considered when you start trying to decide what type of rapid prototyping or additive manufacturing process you're going to be using in your design setting. So again, there's a lot of technologies out there, and you need to have an open mind to not only looking at what you know to exist, but more importantly to what the industry is starting to produce out there, because some of your design requirements or some of your performance requirements may not be directly in line with what you think additive manufacturing is able to produce for your ultimate goal or your ultimate end product. Again, 3D printing is changing the way we go about product development and product manufacturing. At one moment in time, it was strictly used for creating the concept models and what we call traditional prototypes, but we've gone beyond that. With additive manufacturing and material sciences, we are now able to have machines that produce parts faster and get closer to end user customer parts. When you're starting to look at a machine or start looking or considering a service bureau, either internal or external to your organization, there's some new variables that are coming down the line as far as like, where do you get your parts from? Most importantly is the controls that the various systems have on them based on their ability to produce a consistent product. Some systems are very small in nature and low cost, very affordable, down to as low as $300, to other systems that are extremely expensive. But you kind of pay for what you get when it comes to selecting the machines or the process of what you're getting. For example, the IDEA machines, those are considered to be the lower, $500 to $3,000 class machines. Those are what you will find in your typical high school, college, university, at the end of a row of desks in an engineering office. They're designed to get something in your hand quickly and allow you to make very fast design decisions to go back to your engineered process. When you get into the design series, that's where you're investing a little bit more money, anywhere from $50,000 to $250,000. These machines, again, have a variety of materials and different processes that can be used, but each machine has its different strength and weakness, and you need to have a better understanding of what these equipment are able to produce. And the thing that I strongly suggest is if you make the decision that you want to create production-ready parts, things that will be actually used by the end consumer, take the time to go out and see the equipment in action. Take a look at how other customers are using these technologies and gain an understanding of the entire workflow process. In some situations, somebody will tell you that a 3D printed part will take about 20 hours to build in a build chamber, but in reality, when it comes to post-processing, like for example in a SLS type of process where you're doing centered metals, sometimes the cool down in the post-processing process takes longer than the actual build cycle. So again, going to what I was talking about before, go outside of your industry, take a look at what other people are doing, get a feel for how people are using these technologies and how they apply to what you may want to do within your own engineered environment. Whether it's designing the actual end product, in some situations you'll be designing tooling or limited run injection mold or limited stamping dies. In some situations you'll be printing an actual part and you'll be metal plating it, painting it, polishing it. All depends on what your individual given use case might end up being. The biggest thing that everyone on this call needs to keep an eye on is the materials that are being used out there in industry. Although the bulk of my experience has been with PolyJet machines and FDM machines, new delivering mechanisms are creating more of mini robotic work cells where you're combining extrusion process with painting processes and plating processes all being done simultaneously. There's built-in processes in the metal sintering device systems that are coming out in the marketplace where they're using what's called direct energy deposition, where you're using a traditional FDM style printing with an alternative energy source to burn off unnecessary material to get new mechanical properties that you may want to get out of your final part. All this, like I said, is changing every day. So if you're an industry expert or you consider yourself a subject matter in 3D printing and additive manufacturing, and you haven't been to a trade show or attended a user symposium in the last year, probably your knowledge and your understanding of what 3D printing is capable of doing is grossly, grossly out of date. There's a lot of things coming down the market, and it's going to directly impact and change the way you take that CAD data that ALTAIR engineering is creating, those inorganic shapes, those obscure things that never were able to be fabricated in the past, and be able to get them into the hands of your consumers and then into the hands of your engineer and be more successful. So with that, I would like to wrap up and turn over control and address any questions or concerns that the group may have.
Thank you very much, Dave. That was fascinating, and what was great is that it was a great fit with what Ravi talked about. He talked more on the design, and you talked about the different manufacturing techniques. Let me start off, if you don't mind. How do you? Is there a set of guidelines or something that the users can kind of at least get them in the right direction in terms of what type of machine to use and what type of material to use based on the part application that they may have?
And I think you just answered your own question there. It all depends on the application that you have. The application will drive what machine you ultimately pick to do your 3D printing. In Ravi's presentation, you would notice that when he had the vehicle body that was designed using an optimization structure, he did not necessarily print out that body in the final metal part of what it was ultimately going to be produced. He created scale models of smaller plastic parts that were being used for design reviews. So in that situation, even though the ultimate part is a metal part, you can use plastics or SLS or SLA type processes to cost effectively share design intent. In some situations, you could use 3D printing to create the tooling or the check fixtures that will ultimately use to fabricate the final product. So don't think about 3D printing just for the product that you're designing, but also to be a component in the manufacturing and engineered process.
So are you planning to develop like design rules for multiple applications in additive manufacturing?
Well, in that scenario right there, ISO ASTM 52900 standards was created and released in 2015, which basically should be a message to everybody that industry and industry standards are actually behind the curve. One of the biggest problems with additive manufacturing has to do with quality control and the ability to control the actual products that are being produced by 3D printers. Many of these products have shelf life to them. The materials that are being used have a shelf life component. Post-processing, if not controlled properly, could dramatically change the material properties. And the industry needs to catch up with putting standards and quality control metrics in place. Simply stated, there's not enough controls out there, especially if you start using third-party print organization or service bureaus that are outside of your control.
Yeah. Ravi, in ALTAIR software, the rules that the software apply for optimization, is there a standard around that, or is that something what ALTAIR developed?
This is that's a very open-ended question, but I'll answer it. The topology optimization, a lot of people today claim that they can do generative design or topology optimization, but many of them, the topology, the way it grows the structure is based on the rules you specify. You can, the reason why ALTAIR is a leader in this space is because we understand manufacturing constraints much better than anybody else, and we have put it in the within our algorithm to grow the structure in a format that is following the rules. For example, if you are, and as David was mentioning earlier, there's a lot of hybrid. Let's take one step backwards. There's a lot of hybrid techniques as well, where you can print certain materials and plastics and then use it as patterns for traditional castings, which you cannot for investment casting, for example. You can create pattern, you can 3D print the patterns in plastics or certain PMMA type of material that would melt. And the investment casting process is, you dip it into a slurry of sand and it sticks to the surface, you put it in the oven, the wax melts off, leaving the cavity, and you pour standard casting into it, right? So now, depending on the manufacturing process, you can dictate, and that's why we are leaders, because we have all manufacturing constraints. Now, suppose you are doing a traditional casting and you say, hey, I want to do a traditional casting and I want to create a structure that does not have any undercuts. So you can specify draw constraints. So not only will it not have any undercut, but it will also create a taper so that you can extract the pattern out of the casting. Now, the same thing for additive manufacturing. We have introduced overhang constraints, which basically say, if you specify the overhang constraint, the structure will never violate the 45-degree angle that you might have specified, which means that you'll never have issues when you're creating those structures. So it's a combination of understanding what the manufacturing requirements are. And I would also point the people in this call to there's some fantastic repository board on 3D Hub's website where there is a lot of rules that are put together in terms of whether it's plastics, in terms of what kind of thicknesses different types of printers can accommodate, what are the tolerances that, depending on the surface quality, depending on the tolerance that you have in your part, depending on the performance requirements, depending on the volume of production. There is multiple criteria that's there on the 3D Hub's website to guide you through certain design rules. But we are incorporating many of these rules within the way you can direct the structures to grow. So to answer your question, yes, and that's the reason why we are the leaders in this space, because we understand and we have incorporated all of them into our numerical methodology to grow the structures.
And I'd like to interrupt and compliment on Ravi's recommendation of the 3D Hub's publication. It's called the 3D Printing Handbook. It was released in 2018. I just got done reading this document. It is an unbelievably comprehensive book on 3D printing methodologies and design constraint, and I would almost say that it should be mandatory reading for every engineer involved with product development and design who will ever touch a 3D printer, which is everybody.
I'm glad you also looked at it, David. I mean, I think that's a great repository of information.
Yeah, Shashank, let's put that when we send a note out to all of the attendees.
Yeah.
Let's put that reference in it.
Can you repeat the 3D? What is the website address?
The publication is called the 3D Printing Handbook, Technologies, Design, and Application. It's produced by the organization 3D Hubs, and it came out in 2019. I mean, sorry, 2018. Can't get ahead of ourselves.
Yeah. Okay.
And
are there any questions? Oh, sorry. Go ahead. Yeah. I was going to ask if there are any questions from other attendees.
Yeah, I have unmuted everybody, so you can either speak up or you can also type your questions in the chat.
Okay. If not, I have a question for Ravi. Ravi, is the nesting of the parts in the machine, is there a optimization or a simulation that you guys do to be able to nest? Because it seems to me, especially when it comes to holding the parts and the structure required while you're producing the part, and then optimizing all the different parts that can go in the machine at the same time, that's a pretty complicated task in itself.
Yeah, I think definitely. I mean, we already do nesting for in our sheet metal component, in our sheet metal solution. We do nesting so that to maximize the material utilization. To us, it's a combination of right now we do nest similar parts, but we're working on making sure that we have our nesting for dissimilar parts, and also not only 2D but also in 3 dimension. But I would also warn you that, you know, nesting comes with its own problems, because David would probably also elaborate on this, is that especially when you talk, I mean, I think my presentation covered a lot more on the metal printing, and I'm glad David covered more on the plastic and the polymer side. But in the metal side, especially with powder, which is the SLM based process 3D printing, it's also sensitive to where exactly the component is built on, which part of the chamber it is, and you'll be surprised at the kind of differences that you would have in the quality based on where exactly the part is printed. So it's not as cut and dry, and you will have to make sure that you adjust the parameters so that the quality of the parts, irrespective of where it is actually printed, are consistent. Okay, so it's not just a geometric nesting. You have to be very cognizant of heat dissipation in the chamber, because it's also interacting with powder. There's a lot of inert gas flowing through. So you have to make sure that the performance conditions are pretty well captured. It's not just geometric nesting. But to answer your question, yes, we are working on that as well.
And taking that step one further, you know, when it comes time to each individual piece of equipment manufacturer, whether you're going to, you know, through Carbon or Formlabs or 3D or with Stratasys, it doesn't really matter, or EOS or whoever you're using as your equipment vendor, they will tell you the strengths and limitations of part orientations in their machines, because it could directly impact the strength of your ultimate product. And in other situations, part orientation in the build cycle could ultimately determine whether or not your part could even be built at all. In many 3D printed machines, if you have a flat piece that's laying, you know, completely horizontal, it could delaminate against itself off the build tray, and you could have a failed build. Or worst case scenario, you could have a build that would get completed, and you'll have extreme warpage as that part is cooling down. That's a big problem. So part orientation can directly impact your ultimate output of what you get in the part. Right. And again, going back to those standards, just because you designed it to a certain specification, if somebody flips that part 70 degrees, 80 degrees, you could get a completely different result in that final product.
Interesting. We have a few minutes with us, so let's talk a little bit on the business side of things. I think one of the real issues with additive is lead times for part manufacturing. That is why it's been used in prototyping for a long time, but not in production. But it has been the lead times. People are working on it to reduce it. Are there any other ways the industry can leverage additive manufacturing, considering the lead times and some of the other applications, or are there business side of things which can improve so that they can accommodate the lead times that additive has?
Well, I think as far as lead time concerned it's the speed of material deposition, you know, adding more print heads. But the challenges that's happening out there is, as the materials are becoming more and more complex, some of the post-processing time is starting to greatly increase out there. Every machine is different. You have to experiment with different machines to figure out what the lead time ultimately is. And again, I just want to reiterate before, don't think of using 3D printing only for product development. Think of it for being used for tooling, making stamping dies, limited run injection molds, as Ravi said, as patterns for casting operations. You could continue using traditional manufacturing methodologies to get production parts, leveraging 3D printing to get to market faster. And in some situations, we have found that customers will use a limited use mold or die that was 3D printed to prove out a traditional mold or die that would be ultimately used in mass production type operations.
Yeah, certainly tooling is one of the primary applications, and
Yeah.
we are, like, with the COM team, we are exploring that. We'll be going to Oak Ridge, which National Labs, which is really interested in tooling side of the things for additive. Another thing is talent and skills, and David, you have been involved with the talent and skill issues in Michigan a little bit. Can you elaborate on what you and your company is doing to get people interested in manufacturing, especially when we have such advanced technologies like additive?
Yes, one of the things that is going on right now is what's called the professional apprenticeship movement. As many of us may be aware, traditional apprenticeship movement is where you taught someone to be a pipe fitter, a welder, or an electrician. Professional apprenticeship programs that have come out and is being funded by the U.S. Department of Labor is training people to be a CAD operator or an additive manufacturing professional. The reason why apprenticeship training is so nice is because it combines on-the-job experience with classroom training, and it can be modified on the fly. Unfortunately, in university and college situations, they don't have the luxury of being able to adopt and teach new technology in a very fast manner. Usually there's a 3 to 4 year lag time about what's being taught to the next generation employee, whereas apprenticeship training and certification-based training is becoming the new way to leverage current technology and new experimental manufacturing techniques in the most cost-effective way. In the state of Michigan, Governor Schneider released what's called the Going Pro Fund, which is funding workforce development and on-the-job training for new technologies to the tune of $29 million. Decide Solutions has a professional apprenticeship grant with the U.S. Department of Labor where we have $3 million that could be awarded to companies that are interested in training engineers and designers leveraging next generation technologies like what you see with ALTAIR engineering.
Ravi, what are your thoughts? What is ALTAIR doing to train people? You have state-of-the-art softwares, and you are continuously working on improving technologies and adding features. How do you train people so that they first of all they know of this thing and they know the capabilities that your softwares can achieve?
Yeah, I think we have an extremely compelling. In fact, most students and most premier institutions in the country have access to ALTAIR's tools for free. In addition to that, we have an ALTAIR University website where we have our ebooks, demo models. They can download our software and then get access to all our software for no cost. Second, bringing in technologies. One thing I do want to mention is that in general, manufacturing is pretty boring for young kids. Okay, to attract, especially the wind is always blowing towards the west all the time. But one of the things I've noticed in the last few years, and maybe Dave can elaborate on that as well, is that additive manufacturing seems to be attracting a lot of young people because of the coolness factor, and as well as the freedom that it gives youngsters to design things, whether it's making their own jewelry or creating. And we're seeing a lot of that interest coming from racing teams across the world. So ALTAIR sponsors a lot of racing teams where they're pushing the limits of additive manufacturing, whether it's hybrid or direct metal printing. These kids are not only pushing the limits of technology, but they're really excited to use the latest and the greatest to push their vehicles. So we are involving ourselves in a lot of these design competitions as well as the racing teams across the world. And I do see that additive seems to be really bringing back the kids into manufacturing. Do you agree, Dave?
Oh, absolutely. Absolutely. And I think we also have to take a look at entrepreneurship. At one point in time, to become a car manufacturer became not an option for people. But with additive manufacturing, it makes it a lot easier to get into that space. Entrepreneurship is the biggest thing that's driving the economy today. With access to engineering software like the SolidWorks application, the ALTAIR solid thinking application, the tools that are designed out there that's available to people is easier to use and more powerful than ever before. And the ability to fabricate one-of items allows you to get in front of private equity and venture capital people with something that actually looks and performs like the final product that the consumers are actually going to end up buying. It is changing the way companies are coming to market with new innovative ideas. And this generation, it used to be 3D printing was something obscure and unique. Next week, Friday, I believe it's October 5th, is National Manufacturing Day. I'm a little bit struggling with what I'm going to show the kids in my 3D printing studio because they already know almost as much as I do about what 3D printing is capable of doing. It's just that they want to have access to bringing their ideas to market. And I think that we can help enable this next generation.
Yeah, with that, thank you, Ravi and Dave. Are there any last quick 10, 15-second thoughts that you want to leave us with?
This is Dave Derbyshire from Decide Solutions. If you ever find yourself in downtown Pontiac, stop in and see our 3D printing studio in action and walk away with some good ideas on how you can apply it to your business and your products.
Yeah. Ravi, do you have any final thoughts?
Yeah, I think additive manufacturing has the potential to completely revolutionize and put a new renaissance, especially in the Detroit and the Michigan area, because the knowledge of manufacturing has never been, and the power of hybrid manufacturing and with the advent of automotive, electric vehicles and other new vehicles coming in, and the engineering talent in the region, I think we will see a genesis of, and I just saw that Detroit is in the top 6 countries and today for all the startups to move in the US and in the world as well. And I do see that AM, additive manufacturing, has the potential to bring the luster back to Detroit, and I strongly feel that. And we are sitting on a cusp, and our technologies are ripe, and it's the freedom is what you can do is limitless today, and I think we're just getting started.
Absolutely. The more I learn, the more I realize how little I know about the subject, and I think we need to continue the conversation and explore other times and when we can expose more of our affiliates as well as others to the subject. So thank you very much. With that, we're going to close up and
just one final thing that this presentation would be available for all of our affiliates in the affiliate portal and as well as in the COM portal. So if you have the login access, you can always go in there and download it for your reference. And I think you will also get an email from Katie with a link to download if you're on the mailing list.
All right, and thank you, and have a great weekend.
Thanks, Abe and Shashank, for setting this up.
Thank you.
Thank you. Have a good day.